Hello, Prep for Cal students. We're going to be starting on your Exam 3 review. On this Exam 3 review, we're going to be looking at concepts for your exam. However, this is not exactly the exam questions, but this will give you a strong start to how we're going to be able to solve problems on your exam. So, with that being said, let's start on your question 1. For question 1, we are going to be finding the following for the rational function g of x equals 3 times x plus 8 times x minus 1, all divided by x squared plus 6x minus 16. So for part A, we're going to be finding intercepts. So for intercepts, we're going to do g of x set equal to 0 equals this equation in order to find your x-intercepts. So for that, once I do that, I do know that this bottom can be factored to x plus 8. We can also do x minus 2 in order to get this function after we FOIL out. So for that, now that it looks like that, let's see what cancels out as well to see if this makes this process easier. So with that being said, it seems like our x plus 8 cancels out, and that gives us a great motion on what we should do to do this. So if I do that, I have this, and then I have this on the bottom, x minus 2. So let's times this over to get rid of that. And then I have it equal to this, and now we see that x equals 1, which that gives us our x-intercept. So now we need to find our y-intercept. And for our y-intercept, we just want to plug in zeros for our x's to see what that gives us. And that should be what your y-intercept is. So 0 plus 8. And then we also have 0 minus 1. And then we also have 0 plus 8. And we also have 0 minus 2. And that will give us 3 times 8 times negative 1 over 8 times negative 2. And with that, this will cancel out. And then we'll have negative 3 over negative 2. So then your y-intercept should equal, which is y equals 3 halves. So that's your y-intercept. So now that we have found your x and y-intercept, we now can put our answers over here. Our x-intercept will be x equals 1. And our y-intercept will be x equals, not x. We want to have it to be y equals 3 halves. So now let's move on to your vertical and horizontal asymptotes. For your vertical and horizontal asymptotes, we will want to look at this graph and see how the top and bottom have configurations. So this kind of also plugs into how we get these holes in these graphs. So as you see earlier, we canceled out this x plus 8. And with that x plus 8, that is indicating that we have a hole. So, and when we set this bottom equal to 0 to find our VAs, we don't want to include this 8 because that shows there's a hole and not a vertical asymptote at that point. So vertical asymptotes, we set the bottom equal to 0. So then we have this x plus 2 equal to 0, and this shows that we have a vertical asymptote here. Then we need to look for horizontal asymptotes, which will be given by the degrees of this. So if we expand this top part out, x plus 2, 8, and x minus 1. So if we expand this out, all of this out, we have 3 times, let's just do these first. We have x squared plus 9x minus x minus 8. So then we have 3x squared, and then we have these combined together, which will give you 8. So then we'll have 3 times 8, which will be 24x, and then we'll have minus 24. And then this bottom, if we had already as x squared plus 6x minus 16. So now we just need to look at the powers here. So for powers wise, we want it to be, if they're the same power here, which they have the same degree as 2, then that means that we just need to look at the coefficients in front of here. There's technically an imaginary 1 here, so then it'll be the 2 coefficients, so we'll have 3 over 1, so that'll be our horizontal asymptote. So for our horizontal asymptote, we have that. Now, if we were looking for the horizontal asymptote of another function, so if let's say we had 1 over x squared, where the degree is bigger on the bottom, or another example of x over x squared, if the degree is bigger on the bottom, that means that this will have the function go towards 0. Because when we take limits of these, this will go to 0. However, if we had another one where we had the degree where it's bigger on top, we will want this will go to infinity when we do that. So that's how we determine our horizontal asymptotes. So now we finish part A, B, and C. Let's go on to part D with the domain. So now we know that there are problems at x plus 8, which is x equals negative 8. And we also have a slight problem here of undefined at x equals 2. So with that being said, we're going to have to think about this. So if we're looking at the graph, that means there is a hole somewhere here in this negative 8 region, and we also have an asymptote here at 2. So when we do domain-wise, we know that we can come from this way, we'll hit a problem. There won't be a problem between these two sections and not a problem after the two. So then we can say from negative infinity to negative 8. And then we can also union that because we don't want to include negative 8 because there is a problem area there. And then we'll have from negative 8 to 2 because this is a clear area. And then we see there's that problem at 2, so we don't want to define it as it being defined in the function. And then we'll go to infinity. So that's how we complete question 1 for this. So we have x-intercepts, y-intercept. For our horizontal intercept, we have that our horizontal intercept was y equals 2. And for our vertical asymptote, we have x equals 2. And then we have a hole at negative 8. And with that being said, for negative 8, we need to plug in negative 8 here to see where that has that coordinate there. So for that coordinate, we need to put in 3 times negative 8 plus 8, and then we also need to put in negative 8 minus 1, and then we need to do negative 8 plus 8, and then we also need to do negative 8 plus minus 2. And with that, we should get 2.7 as our y coordinate for that. And then for domain, we'd establish that down here as negative infinity to 8, union 8 to 2, negative 8, my bad, and then union that from 2 to infinity. And there we go for problem 1.
Okay, starting with number 2, we're going to find an example of a rational function with vertical asymptotes x equals negative 5, 0 at x equals 3, a hole at x equals negative 6, and the following properties. So we're kind of going to go just one at a time and slowly build upon each one as we go through this. So the easiest one to start with is probably this here, this vertical asymptote at x equals negative 5. So we know that we get a vertical asymptote whenever we have some number over 0. And the way we're going to kind of account for this being negative 5 is that we said, well, if I plug in negative 5 here into this, notice I'll get a 0, which means that this here gives us this property of the vertical asymptote at negative 5. So now let's do the next one, a 0 at x equals 3. Well, what I need is to where if I plug in 3, we get a 0. And for a rational function, the way you're going to go about that is by putting in the numerator. And we're going to say x minus 3. So this way, if I plug in 3 for x right here, this term here will be a 0. And then it won't really matter what the other terms in the numerator are because it'll be a 0. Now lastly, this one might be the trickiest, is that we're going to have a hole at negative 6. So again, just to reiterate, what a hole would be is if, say, like I have some line here, and then at some point in it, there's just like this gap here. And where these come from is usually because we have something like x plus 6 over x plus 6 in both the numerator and the denominator. So you can see that if I wanted to, I could cancel these out, and it would be almost an identical expression. The only difference between this and if I cancel them out is that if I plug in -6, we get some point of discontinuity, which just means basically a hole, or it's just somewhere where we don't have a y value. So then the last part here is that we need to make sure if I plug in, if I go way, way, way out for x, that my y is going to be -2. And if I go out to the left, my y is still -2. So we can kind of, there's a couple ways to go about this. But the easiest is just to see that the powers of these is the same as the powers of these, which means that as we get really far out there, there's not really, it's going to kind of balance each other out. And so the way that we can, and by balance it out, it'll probably go to 1. And so the way that we can fix that is just say, well, if I put a -2 out front, now if I go way, way, way out, then these will sort of equal 1, and we'll have some -2 times 1. But if you wanted to see that more algebraically, because, this is kind of a little bit strange, let's go ahead and just FOIL everything out. So if I get x squared plus 6x minus 3x minus 18 all over x squared plus 6x plus 5x plus 30. So now we know if we want to sort of like take the limit as x goes to infinity, that the highest term is the one that dictates the behavior. The way that we can even see that really algebraically is if we multiply everything through by 1 over x squared. So we can see that we'll have, and I'm going to go ahead and combine these two middle terms. So we'll have 1 plus 3 over x minus 18 over x squared. And down here we'll have similar thing, 1 plus 11 over x plus 30 over x squared. So now we can really see that if x goes to infinity, this will be 0, this will be 0, this will be 0, and this will be 0, and all that's left is 1 over 1, which means that all I have to do is just take this whole thing and put a -2 out front. And now if I take x way far out, this whole thing will equal -2. And same thing for if we plug in negative infinity. So our rational expression, or rational function, is going to be y equals -2 x plus 3 times x plus 6 all over x plus 5 times x plus 6. Okay, number 3, starting with A, we're going to evaluate the following limits. So for this one here, we have some rational expression. If you know that big acronym, Bobo-Botten eats DC, feel free to use that. But because I know not everyone is familiar with that, I figure I'll just go ahead and work out the algebraic way, because you can never go wrong with that. So we get 3x squared minus x plus 1 all over 2x squared plus 5. So the algebraic way is to take whatever your highest powers are and put them over here, and then to multiply both the top and the bottom by 1 over whatever that power is. So we can kind of cancel out these x's here. So we see if we do that, so we get 3 minus 1 over x plus 1 over x squared all over 2 plus 5 over x squared. So now if I evaluate the limit as x approaches infinity, we can start canceling some stuff out. So this term here will go to 0, this term here will go to 0, and this term here will go to 0. Then we'll be left with just 3 over 2, and we're done. And likewise, if you used a Bobo-Botten eats DC, you'd see exponents are the same for this one and this one, so you just divide 3 by 2. Okay, next one, for part B, it's written a little bit differently, but we're kind of going to do the same thing that we did at the last step of the other one, where we're kind of going to jump straight ahead to just plugging in or like sort of evaluating it. And the one thing that we really need to understand is what happens if we have a negative exponent. So x to some negative power, let's just say 1, is the same thing as 1 over x. Likewise, x to the negative 2 equals 1 over x squared, and so on. So if we were to rewrite this, so we have 8 over x cubed plus 5 over x plus 1. And we're already ready to sort of evaluate this limit here. If I imagine plugging in some really big number here, this will basically be 0. So we can just go ahead and say 0. And same thing with this one. And then all that we're really left with is 1. So that's our final answer. Okay, so number 4, we're kind of going to use a similar method that we did on number 2. So firstly, we need to know that there's got to be vertical asymptotes at x equals negative 2 and x equals 3. So I'm just going to say that we know that our denominator of whatever our function is has to be x plus 2 and x minus 3. So this way, whatever we put up here in our numerator, unless it's one of these two, is basically going to be a vertical asymptote. So let's move on to our next step. We're going to have a horizontal asymptote of y equals 0. So this one might be a little confusing, but the best way to understand that is that our bottom part has to be larger than our numerator. So that way, as we plug in bigger and bigger numbers of x, we'll have some number over a much bigger number. And eventually, we just call that 0. So we just have to remember that this part here is telling us that the power, the total power, so here we can see that we have x times x squared, must be smaller in the numerator. So next, g is going to cross the x-axis once at x equals 5. So if we cross the x-axis, that means that we have a 0. So if we have a 0, we put in our numerator x minus 5. So now if I plug in 5, we have that. So lastly, we have to pass through this point here. This is probably the trickiest one. So we're going to go about this is sort of what we did to get this negative 2 here, is that there's going to be some number out in front. We're going to say this equals y. And we have this point that x equals 4, y equals 0.5. So we can actually just go ahead and plug stuff in. So we'll have a times 4 minus 5 over 4 plus 2, 4 minus 3 equals 0.5. So let's start simplifying. So we have negative a over, then in our denominator we'll have 6 equals 0.5. So we get that a has to equal negative 3. Now once we have this, if I plug this back in up here, then that will satisfy this condition, and it won't mess up any of these other ones that we created along the way. So our final answer is going to be that. And instead of y, because it says g, I'm going to say g of x equals negative 3 x minus 5 over x plus 2 times x minus 3. And we're done. Okay, number 5. We're basically doing the same thing, except instead of using numbers, we're going to say a, b, and c. So if it helps you in your mind, just imagine a is 1, b is 2, c is 3. We just want to treat them the exact same that we would any other number. So firstly, does f have any horizontal asymptotes? If so, what are they? So horizontal asymptote is where we take the limit as x approaches infinity and negative infinity, and what we see is that this will do something. And you can use Bobo-Botten, ETC, or you take the limit as x will go to infinity of ax over bx plus c. So just like we did on some of these other ones, we're going to multiply by 1 over x over 1 over x. And don't be scared by the a, b, and c. They're just some number, some constant. So what we find is that we'll have a over b plus c over x. So now if I take the limit as x approaches infinity, we will have just a over b plus 0, or a over b. And could have gotten that from just dividing the coefficients right away of your highest term. So we're going to say yes, f equals a over b. Okay, next one, we're going to look for any vertical asymptotes. If so, what is it? So a vertical asymptote is where your denominator equals 0. So we're going to set bx plus c equal to 0. And from here, we're able to see that x is going to equal negative c over b. So if I plug in negative c over b, we will get a 0 in our denominator, which corresponds to a vertical asymptote. So yes, x equals negative c over b. Okay, number 6, we're going to find the radian measure of negative 100 degrees, and we're going to give an exact answer. So to go from degrees to radians, you're going to multiply it by pi over 180. And I always just remember radians has pi, so you multiply by pi, sort of like a dimensional analysis where you're saying that there's negative 100 degrees times pi radians per 180 degrees. That way you can kind of like imagine canceling out the degrees, if that helps sort of reason things. But so to simplify this, we're going to have negative 10 pi over 18, and then we can cancel out a 2, negative 5 pi over 9. And we can't really simplify anymore, so let's leave it there. Negative 5 pi over 9. And our next one is going to be doing the opposite. This time we're allowed to use a calculator. So we're going to find the degree measure of 5.9 radians. So we're going to have 5.9 radians times 180 degrees per pi radians. So let's get out our calculators. And if we go ahead and type this in, 5.9 times 180 divided by pi, it's going to be 338.04, but if we round to the nearest degree, it's just 338. So 338. Let's make sure that we put this little degree symbol anytime we have a degree. So next, we're going to find the angle that is coterminal with negative 900 between 0 and 360, and we're just going to find a angle between the two. So the way that we do this is we try and add 360 degrees until we're close to there. So if I do negative 900 plus 360, we will have, this will be 500, excuse me, not 500, or yes, sorry, 540, and it'll be negative. Let's go ahead and add another 360, and this here will still be at a negative number. This will be negative 180 degrees. Now if we add another 360, we're at 180 degrees. So this angle is the same as this one, it's the same as this one, it's the same as this one. They're all considered coterminal. It's just that this one happens to be between 0 and 360. So that's going to be your answer here for A, 180 degrees. So now we're going to find two angles in radians that are coterminal with negative 9 pi over 7 with one angle of those angles between 0 and 2 pi. So to be coterminal, if we imagine drawing a unit circle, so negative 9 pi over 7 is just a little more than pi, or I guess a little less than negative pi. So you come over here around, so that's negative pi, and you go a little bit more, so somewhere around here. So you can imagine that this angle is something like that, this angle. So it's going to be coterminal if I go all the way around 360 degrees. So that's one way that we can do this. So if I do negative 9 pi over 7, and then I go ahead and add 2 pi to this. So this will be the same thing as negative 9 pi over 7 plus 14 pi over 7. So this is 5 pi over 7. Oops. All right. So that's one angle. And if we want another coterminal angle, well, we just go all the way around again. Sure. So let's add 2 pi to this. If we do that, that'll be the same sort of procedure where we're just going to turn this into 14 pi over 7, so that way they have the same denominator. We'll go ahead and do 21 pi over 7. So this is also coterminal. And we're done. Actually, I just realized I made a quick little mistake. Instead of 21, if I do 5 pi plus 14 pi, as 5 plus 14 is 19, not 21. So this will be 19 pi over 7. That's my bad. Okay, now next one. Okay, number 9. Tom has a central pivot sprinkler that uses a rotating sprinkler head. He wants to plant a garden that covers this area. Our radius is 20 feet. This area is 420 feet. And we want to know the perimeter of this shape. So we need this side, this arc, and that side. So we know that area of some sector is 1/2 theta times r squared, where theta is measured in radians. So we also know that 420 equals 1/2 theta times 20 squared. So now we can solve for theta. And if we do this, we should get that theta is going to be 2.1 radians. So next, we need to figure out this length here. So this length, we'll call S, is going to be equal to R times theta, which is going to be 20 times 2.1. So we find that this length of this arc is going to be 42 feet. So we know from here to here is 42. Let's draw this in some. I have to excuse my poor drawing. 42 feet. So that's part of our perimeter. We also have this, which is 20 feet, and this, which is 20 feet. So now if we put all of these together, this is going to be 82 feet. And we're done. Okay, number 10, we're going to name the quadrant in which negative 11 pi over 9 lies and find its reference angle in radians. So if I sketch out just a quick circle, negative 11 pi over 9 is just less than negative pi. So if we go around backwards, so that will be negative pi, and then we go a little bit past it. So we should expect that our angle is maybe something like this. Which is nice because now we know that if I find the coterminal angle here, that will be the reference angle. Or well, it'll measure it from here, and then we'll just have to get that part there. So, and really this is measuring it like that. So the quadrant in which it lies is quadrant 2. Now, in order to find the reference angle, generally a good place to start is just to get it between 0 and 360, or between 0 and 2 pi. So to do that, I'm going to add 2 pi to it. So negative 11 pi over 9 plus 2 pi. It's the same thing as if I did negative 11 pi over 9 plus 18 pi over 9, which is going to be 7 pi over 9. So now I know that if I go from here to this angle, that's 7 pi over 9. But the reference angle is from this to the nearest x-axis. So for this one here, it's just going to be whatever this angle is. But I know that from here to here is pi, and from here to here is 7 pi over 9, so the difference of those two is going to give us our reference angle. So we're going to do pi minus 7 pi over 9. So we need to have a similar denominator, so we're going to make this 9 pi over 9 minus 7 pi over 9. So now we have that our reference angle is going to equal 2 pi over 9, which represents just the distance from here to here. Or here to here, sorry. So 2 pi over 9. In number 11, we're going to find two different angles that lie in quadrant 2 and have a reference angle of 3 pi over 13. So if it's in quadrant 2 and it has a reference angle of 3 pi over 13, it might be something, let's say that this measurement here is 3 pi over 13 as a reference angle. So we might see some different angle, maybe kind of like this here. Or we're going to go all the way around like that, and that will be our angle. So we know that this here is 3 pi over 13. So now let's figure out what this theta is here, because that's going to be one of our angles, and we can just find a coterminal angle from there. So I know that from here to here is pi, so it's going to be just short of that. So it's going to be pi minus 3 pi over 13 should equal our reference angle. So we're going to have 3 pi over 13 minus 3 pi over 13. So if I solve this out, I get that theta is going to equal 10 pi over 13. So now I know that this here is 10 pi over 13. So now I just need to find a coterminal angle with this 10 pi over 13. So I guess a good place to start is just to add 2 pi. So if I do that, that will be 10 pi over 13 plus, since I need to have the same denominator, 26 pi over 13. So another angle might be 36 pi over 13. So here's another angle that we can use. Oops, why did I write that? And we're done. Okay, number 12. Oops. If cosecant is greater than 0 and cotangent is less than 0, in what quadrant will the angle theta lie? So what we need to remember is all students take calculus. And this is just a way to kind of remember the signs of everything. So all your trig functions are positive in this quadrant. Only sine and its inverse is positive here. So cosecant is 1 over sine, so that one will be positive here. Only tangent and cotangent are positive here, and then only cosecant and secant are going to be positive here. And we can always remember that cosecant of some angle theta is the same thing as 1 over sine for that angle. So if we just look for wherever sine is going to be positive in this case, we can see where cosecant is going to be positive. So we can see that that's going to be for this quadrant right here, quadrant number 2. And now we check for cotangent to be negative, which also is fine in this quadrant, because cotangent is theta equals cosine of theta over sine of theta. And while sine of theta will be positive in this quadrant, cosine of theta will be negative. So you'll have some positive over some negative, so it will be negative. So that just means that our the quadrant with both those characteristics for cosecant and cotan is going to be quadrant number 2. Okay, 13. We're going to assume angle A passes through point A, B through B, etc. We're going to rank the values of the trig functions. So starting with sine of A, well, I guess starting with sine. So sine is going to be equal to some angle theta. It's going to be, we can sort of imagine it as y over our radius on the unit circle. And fortunately, we say that our radius is 1 on a unit circle. So whenever we say the largest and smallest sine theta, we're really looking for the largest and smallest y value. So we can see the largest value should be for this one A, I'm going to say that A is slightly above B. So that means that sine of A will be our largest value. Next, we can look for the smallest one, so we should start looking down here. So E here is the most negative. So that one here is going to be our smallest sine value. E, just because, again, sine is going to be our y-coordinate. So next one, we're going to do cosine. So cosine on the unit circle is going to be x over r. In the unit circle, our radius is 1, so it's just going to be x. So whenever we say what is the largest cosine of some angle, that's the same thing as saying what is the largest x value at that point. So you can see that this one here, f, is going to be our furthest to the right, or our largest x value. So cosine of f. And then the smallest one is going to be the one furthest to the left, the most negative. So you can see that one is here at c. So that one will be our smallest value, cosine of c. Okay, 14, we're going to find the exact value of each of the given trig functions of theta for this particular triangle. We're going to give exact values. We're not going to use our calculator at all. So firstly, starting with sine of theta. So sine of theta is going to be the same thing as opposite over hypotenuse. So if we look at our triangle here, this is our opposite side, so I'm going to label it O for the time being. And this is our hypotenuse here. So we don't know what our opposite side is, but we know that our hypotenuse is 10. So we need to actually solve for what this opposite side is. So we can use that. If we have two sides of a right triangle, we can find, oh, my bad, I just realized theta is actually right here, which means that our adjacent side is actually the one that we need to solve for. So look, our angle is here, which means that our opposite side is this side right here, which means that we have everything that we need. We have our adjacent, our opposite, and our hypotenuse. So sine of theta is going to be equal to our opposite side 9 over our hypotenuse of 10. So sine of theta is 9/10. Now for cosine, now we have to solve for this side, which we can use using Pythagorean's theorem. So we're going to take our adjacent side squared plus our opposite side squared, so 81, equals the hypotenuse squared, which is 100. So we get that the adjacent side squared equals 19. So then from here, we say that the adjacent side is going to be square root of 19. So I'm just going to put equals square root 19. So now, if we look for what we're solving next, cosine of theta is equal to the adjacent side over the hypotenuse. So now we know that our adjacent side is square root 19, and our hypotenuse side is still 10. So that's going to be our answer for this one. And we don't really have any simplifying that we can do, so we can just leave it there. And lastly, tangent is going to be opposite over adjacent. Tangent, so angle theta, is going to be opposite over adjacent, which for us is going to be 9 over square root 19. And there is technically a little simplification that we can do here, because we don't really like square roots in our denominator. So what we can do is take this and multiply it by square root 19 over the square root of 19. And if we do that, we get that tan of theta is going to equal 9 square root of 19 over 19. So these two expressions here and here are the exact same. This one's just a little bit more formal, I guess. So let's write this for our answer. 9 square root 19 over 19. And that will be our answer. Okay, 15, we're going to find the exact value of each of the following and give reasons, including the quadrant in which it lies and its reference angle. So I went ahead and put this full unit circle here. So starting with tan of 5 pi over 6, let's see if we can find 5 pi over 6. It's going to be a little less than pi, so yeah. So tan of this angle that goes from here all the way around here. So tangent is sine over cosine, and we know sine is our y value on the unit circle and cosine is our x value. So tangent of some angle is going to be y over x. So you can see here that our y value is 1/2 and our x value is negative square root of 3. So we can go ahead and say that tan of 5 pi over 6 is going to be 1/2 over negative square root 3 over 2. And we're able to do a little bit of simplification by canceling out this 2 with that 2, and we will just be left with 1 over square root of 3. This will be negative. So let's write the exact value of this is negative 1 over the square root of 3. And we know it should be negative because in the second quadrant, tangent is always going to be negative. So lastly, we just need to find the reference angle, which is going to be the angle from here to here, which we can see is going to be pi over 6. But if you wanted to show that algebraically, it's going to be pi minus 5 pi over 6, which is going to be just pi over 6. So our reference angle is going to be, I'll write quadrant 2, therefore less than 0, and the reference angle is pi over 6. We'll call that good. So next one, we're going to do a similar process. We're going to do cosecant of negative 2 pi over 3. This time, we'll have this unit circle here just in case we need it. Let's try and reason through this one without the unit circle. So firstly, let's try and figure out what quadrant we're looking at. So, and this one here should be like that. So if we were to start right here at 0 degrees and go backwards negative 2 pi over 3, well, that's just less than pi, so we should be somewhere within this area. Maybe something like that, which means that we know that we're in quadrant 3. So we should expect cosecant to be negative. Therefore, we will be less than 0. So now let's figure out what this reference angle is. And I think the best place to start is to get the coterminal angle that's just positive of this. So we can do that by figuring out negative 2 pi over 3 plus 2 pi. So this is going to be 4 pi over 3, which means that if I was to start here and go all the way around to my angle here, that value is 4 pi over 3, which is the same distance as going this way. So now let's figure out here what our reference angle is. So the reference angle is going to be the distance from here to here, and we know from here to here is pi, and that from here to here is 4 pi over 3. So we should be able to reason out that 4 pi over 3 minus pi is going to be our reference angle. And in this case, that is going to be pi over 3. So we have a reference of pi over 3. So now let's see if we can figure out the value of it. So firstly, we know that, cosecant of some angle theta is going to be the same thing as 1 over sine for this angle. So we just need to figure out what sine of our reference angle is really. So sine of pi over 3. See if we can do this without looking at our unit circle. I know it's right there, but so the way that I like to remember them is that break it into 3. So the smallest is going to be pi over 6, and then the next is pi over 4, and then pi over 6. And you just have to remember that this middle one here is root 2 over 2, and root 2 over 2. And then you see that your values here just sort of count up and down from there. So this lowest one we know has a larger x coordinate, so that one is going to be root 3 over 2, and then square root of 1 over 2, which is really just 1/2. So that's sort of the way that I go about memorizing the first quadrant, because memorizing the first quadrant on the unit circle is very useful. Then we know the same thing follows here. So this one is going to go down some, this one is going to go up because we're less x, more y. So that's going to be 1/2, comma, root 3 over 2. So now, if I was at pi over 3, which is this top line right here, I know its coordinate is going to be this. And if you wanted to, you can always just pull up a unit circle, but if you don't have one for whatever reason, knowing this first quadrant can really help you figure out anything else on the unit circle. So from here, we just need to figure out, okay, well, sine of pi over 3 is going to be our y coordinate, so that's going to be root 3 over 2, root 3 over 2. So, but we're really looking for cosecant, which means that we're going to take 1 over this and say that cosecant of pi over 3 is equal to root 3 over 2. So now the whole reason why we did this is because we basically found, it's probably not drawn the best here, but the angle that's opposite of this shares the same reference angle, which means that its y value is going to be the same, but negative. And same thing for any of these other quadrants. So say like we had this angle and it had this much reference angle, and we compared that to pi over 3 with whatever it be in the fourth quadrant, it will also have the same x and y value, except one of them will be negative. And in this quadrant, we can see that the y value is negative, x is positive. So now if we know that, we can go ahead and say that because we're in quadrant 3, both of these are going to be negative, which means that cosecant of 4 pi over 3 is going to be negative square root 3 over 2, and then put 1 over that. So our answer should be, because we know we're in quadrant 3, we're less than 0, negative 2 over the square root of 3. And that should be our answer. Let's check. Yes. So now, if we wanted to, we can also go check this with the unit circle. So we know we're at 4 pi over 3. See, I drew it a little off. So we'd find this point here. We'd say, okay, cosecant is 1 over sine. Our y value here is this one. So what is 1 over this one? Well, that's going to be this. And then we'd be done. But if you didn't have the unit circle, it's really helpful to use your reference angles and just have this first quadrant memorized.